So welcome back to this class. So in the previous session, we demonstrated a problem on how to evaluate a limit of the function f of x equals to sin x over x. And we gave the informal definition of a limit. In this session, we are also going to give more examples on how to find limits of functions by graphical and numerical approach. So the first problem. So investigate limit as x approaches 9 of x minus 9 over square root of x minus 3 graphically and numerically. Now, for this problem, so our solution, we see that if you try to do direct substitution, replacing 9 where there's x in this function, so x minus 9 over square root of x minus 3. If we replace x for 9, we have 9 minus 9 over square root of 9 minus 3, which is 0 over 3 minus 3, which is 0 over 0, undefined. So direct substitution gives us a fraction that is not defined. So we don't divide by 0. So therefore, what we do, we try to find the behavior of the value of this function as x gets closer and closer to 9, both from the left of 9 and then the right hand side of 9. So you see, if this is an ampersand, then this is 9. So this we have 10, and then we have here we have 8. So what we do, we try to get values of the function as we move from, say, 8 going to 9, and then moving from 10 going to 9, but not necessarily at the point 9 itself, because we have seen from this point here that the function is not defined at the point 9 itself. So we draw a table. So say x approaching 9 from the left. So remember, the negative sign just to show that left doesn't mean that now you're making 9 to be negative 9, making the value 9 to be negative. So then negative, and then the value of the function f of x, which is just x minus 9 over root x minus 3. And these have another table, x approaching 9 from the right, and then let's see the value of the function as x approaches 9 from the right. So then we can pick values like, say, I pick 8.9, and then 8.99, and say 8.999, and then say 8.9999. So pick those values, so values which are very, very close to 9, but not 9 itself. And then this other one, you pick, say, 9.1, and then pick 9.01, say 9.001, and then 9.0001. Using your calculator, when you put x for 8.9, you'll get the answer will be 5.98329. When you put x for 8.99, you get 5.99833. When you put 8.999, you get 5.99983. This other one gives you 5.9999833. So as you observe these values, you see that these values are moving closer to the value 6. And when you put 9.1, you get 6.01662. This other will give you 6.001666. This other will be 6.000167. And this other will be 0.6.0000167. Also, this one, if you round off to nearest whole number, then this also roughly 6. So therefore, we can say limit as x approaches 9 of x minus 9 over square root of x minus 3 is just 6. Because all these values, if you try now even to make these values be closer to 9, you'll get that the number is approaching the value 6, both from the left and then from the right. And on a graph, if you draw or sketch the graph, this x, so say this is 3, this is 6, this is 9, 12, 15, 18, 21, 0. So say this is 3, 6, 9, and then this y. If you draw the graph of this function, this is how it would be appearing. We have actually it's not defined at 9, then that's how it will be looking like. So the function is not defined at 9, but then the value at 9, the value is approaching almost the value 6. So that is that's a confirmation that really the limit, you see, though the function is not defined at 6, but then at 9, but then the value of the function you draw the graph is roughly the value 6 in the y-axis. And then example 2, investigate a limit as x approaches 4 of x squared. So this one, you draw a table of values. So draw a table of values, say x approaching 4 from left, and then f of x, which is x squared. And then we have x approaching 4 from right, and then f of x, which is still x squared. So we'll have, say, pick 3.9, 3.99, 3.999, say 3.999. You pick these values to be very, very close to this number A. And then say this is 4.1, 4.01, 4.001, and then 4.0001. When you put in the function 3.9, you get 15.21. This gives you 15.9201. This gives you 15.992001. This gives you 15.9992001. You see this value is roughly approaching 16. And then this other will give you 16.81, 16.0801. Then this will be 16.008001. And then this 16.0080001. This is still roughly approaching the value 16. So therefore, we can say limit as x approaches 4 of x squared is 16. And if you draw a graph, for this, you see this a quadratic function. So this is how it looks like. Y equals to x squared. And then at 4, we'll find that the value on the y-axis is 16. So therefore, limit of x squared as x approaches 4 is 16, because you see we approach the same value from left, we get 16, and also from right, we get 16. And then number 3, example 3. So investigate limit as h approaches 0, e raised power h minus 1 over h. So we'll do the same thing. So have solution. We have our table of values for h, and then so this, in terms of h, we call it f of h. So you say we start with, so h approaching 0 from left, and then we have h approaching 0 from right, so f of h. So say I pick a negative 0.02, and then negative 0.005, and then negative 0.001, negative 0.0001. Remember, you pick those values which are very, very close to the number that you have, so that you get the trend properly. So this, when you put the function, you get 0.990. This will give you 0.99750. This will give you 0.999500. This will be 0.9999500. You see, these values as move closer and closer to 0. This is approaching 1. And then for this other one, you pick 0.02, 0.005, 0.001, 0.0001. When you put into the function, this will give you 1.0101. This will give you 1.00250. This will be 1.000500. And this will be 1.0000500. So you see, these values are just roughly approaching 1. So therefore, we say limit as h approaches 0 of e raised power h minus 1 divided by h is just 1. And then if you are to draw the graph, this is how the graph will look like. This is x, this is h, and then this is the y, which is f of h. So the trend of the graph is this, so it's not defined at 1, but then that's how, this is how it looks like. So this at 1. So you see, from both from left and from right, we have the value is approaching 1. So this is 0. So therefore, limit as h approaches 0 of e raised power h minus 1 over h will always be 1. And then lastly, let's now demonstrate what limit that is not defined, or limit that doesn't exist. So example 4, investigate limit as x approaches 0 of sine pi over x graphically and numerically. So here, so solution, one thing that you need to know that if you put directly 0, then this will not be defined because we have pi over 0. We don't divide by 0. So sine pi over 0 undefined. So therefore, we need to investigate the values of the function closer to 0. So let's have a table of values. Say x approaching 0 from left, then f of x. And then we have another table, x approaching 0 from right, and then f of x. So you can pick values like, say, negative 0.1, negative 0.03, negative 0.07. Please, there's nothing special in these cases, but what is supposed to be done is that you pick the values which are very, very close to that number 0. And then negative 0.0009, say negative 0.00065. So these are values which are very, very close to 0 from the left. So when you put into the function, this will give you 0, this will give you 0.866, this will give you negative 0.434, this will give you 0.342, this will give you negative 0.935. And then as x approaches 0 from right, say 0.1, 0.03, 0.007, 0.0009, 0.00065. So this will give you 0, this will give you negative 0.866, this will give you 0.434, this will give you negative 0.342, negative positive 0.935. You see the values here, this just the sign of these values we have picked here are opposite of the signs of the values we have picked here for the same x values. So you see, these values you can't actually predict to say that the values of f of x as you move closer and closer to 0 is approaching any given value. These values are oscillating. Since the values of f of x oscillate between +1 and -1 infinitely, as x gets closer to 0, then we say that we conclude that the limit does not exist. Does not exist. The limit of this function doesn't exist because we can't really predict that the next value of x we pick, even from the examples we have, the few values of x we have picked here, we can't say that now the next value will be having this such number for f. Does not exist. And if you were to draw the graph of this graph, this curve, so this and this, you'll find that this is how the graph looks like. It will be this. So this is how the graph looks like. So this is one, this negative, so negative, negative one, so negative one. So it's roughly something that looks like this one. So this can't tell you the values, the value of the function, how it behaves as we approach it. So actually so here we have more. This is how the function looks like. So they are more concentrated around this place. If we are to draw, they are roughly concentrated here. Then that's what we have. So they are split around this point. So you can't really say that this is a value that the function is going to attain. So y equals to sine pi over x. So the limit doesn't exist. So this does not exist for this given problem. And easily it can be seen from the values we have picked in this table. We can't say that as we move closer to 0, then y or the function f of x is approaching any given value because of these oscillations. So in the next session now, we'll give the formal definition of limit and then do some proofs involving the formal definition. So thank you.